Assalamu alaikum everyone. So lecture number 4, and today we will be discussing about transmission media. So let's start. So these are the bullets which we will be going through one by one. Transmission media, then we have different types of media and their classification on the basis of different metrics. And whenever we talk about the media, transmission media, every media it contains certain characteristics, and we have to take into account the design parameters, the design specification for that media that is going to be used in order to have transmission. And then we will talk about in more details about guided media and unguided media. And as our course is concerned about wireless and mobile communication, so we will talk about different frequencies that are being used in wireless transmission, wireless communication. The antenna, which is a very important component when we talk about wireless communication. So we will be discussing the antenna and finally the propagation and different modes of propagation. So let's start. So first we will talk about transmission media. What is the transmission media and how we can define or describe the transmission media. So actually it is a physical path between the sender and the receiver, right? And we normally talk about the communication between different computers, between different devices that are being used for internetworking of computers and for data communication. So media is defined as a physical path between sender and the receiver, source and the destination, right? So you can have a lot of different school of thoughts regarding transmission media. The signals are transmitted from one device to the other device, right, in the form of electrical pulses if we have the physical media, we have the guided media, or we can also say that the signals are being transmitted from source to destination in the form of electromagnetic radiation or electromagnetic energy. So we have different examples. We can regarding the electromagnetic radiations, so we can use radio waves. There are infrared light, visible light. We can also use visible light whenever we talk about the fiber optics, ultraviolet light, and X and gamma rays. These all fall into the electromagnetic spectra, right? Or you can say they constitute the electromagnetic spectrum. So here is the snapshot of the electromagnetic spectrum. So you can see that not all the portions are being used for telecom in order to have communication between telecom devices. And each portion of the spectrum, it needs obviously a medium, right? So if I talk about this spectrum, so you can see that we have wavelength over here. It is mentioned in meters, and then we have a frequency that is mentioned in hertz. So if we go from left to right, so you can see that the wavelength is decreasing. So here you can see wavelength is decreasing, and on the other hand the frequency is increasing or rising. If we move from right to left, so you can see that the frequency is decreasing, right? From here, let me mark, from here to here, frequency is decreasing, right? And the wavelength is increasing. As the number of waves being made, they are lesser. So here the number of waves are more, so it means frequency is rising. So here frequency is decreasing and wavelength is increasing. If I move from left to right, so frequency is rising but the wavelength is decreasing. So here we have the visible spectrum, right? Okay, then we can classify media into two different types. First is the guided media and the second is the unguided media. So for guided media, we have a physical path, actually physical path, or you can say conductor, right, that is connected from one device to the other device, or physical medium. The examples are twisted pair, we can have coaxial cable, optical fiber, and for the unguided media, or it is normally referred as wireless transmission or wireless communication media, we normally transmit electromagnetic waves without using any physical conductor, right? So the signals are being transmitted in the air, right? Or in few cases we can use water also, the surface of water, or maybe the water itself, right? So we have two different types of media. First is the guided and the second one is unguided. In guided media we use we have examples of twisted pair, that is actually a pair of copper coaxial cable, right? Again it's also a conducted media, but we have different sort of arrangement. Then we can also use optical fiber that is made from the glass or plastic, fine plastic. So when you talk about the classification, the characteristics and the quality of communication is normally gauged by the medium and the signal that is being used. For guided, the medium is much more important. For unguided medium, there are some other factors, other parameters that are important. For example, bandwidth that is produced by an antenna is more important, right? And the data rate is also important alongside the distance between repeaters. So here we have, you can say now we have mentioned different guided media and the unguided media. So you can see in guided we have wired media, and in unguided media we have wireless. So again, twisted pair, coaxial cable, fiber optics, they fall in the category of wired media, and we have air and water or atmosphere and the outer space, they are unguided media and they fall into the category of wireless communication. So moreover, we can also have signals that are having lower frequency, right? So those sort of signals with lower frequencies, they are transmitted as electrical pulses or electrical signals over some conducted media or cables made by metals. But if we talk about the fiber optics, so it is not possible to transmit electrical pulses on fiber optics, or if you want to transmit light onto the conducted media or metal cable, so it is not possible. So there are certain sort of signaling that can be used for certain media. For example, in case of metal cables, you can only use electrical pulses. For optical fiber, you can only use light in order to transmit data. Then we have to take into account certain design parameters for transmission media. So, for example, bandwidth. If we keep all the factors constant, right? So we have also studied and proved that if we have greater bandwidth for a signal, so we can transmit the higher data, right? So you can say that the greater the bandwidth of a signal, the higher the data rate that can be achieved, right? So this is the ideal case. Then there are some transmission bottlenecks, or you can say impairments or limitations. These are the distance a signal can travel, right? So we wish that if we are transmitting a signal from a transmitter to a receiver, it should traverse more distance, right? But there is an upper limit regarding each transmission media. So we have different characteristics regarding the transmission media when we talk about the distance a signal can travel over a transmission media. Then interference, right? So we can have interference due to the overlapping frequencies, right? And as a result, it can distort the signal, or we can have the scenario when the signal is wipe out completely. Then whenever we are talking about the data communication or data transmission, we need repeaters and amplifiers and receivers, right? So if we increase the number of receivers, right, so then it means we are actually introducing more distortion, right? And the limiting factor is the distance or the data rate, right? So we will talk about this in more detail after some time. So number of receivers, this is also a sort of design factor. So here we have summed up the characteristics of guided media, right? So you can see that we have mentioned the frequency range, the attenuation, and the delay, because these are the important factors, and one of the most important factor is the repeater spacing, right? So whenever we transmit a signal for a longer distances, right, so we need repeaters in between, right? So after how much distance we need a repeater for a certain transmission media, right? Okay, so here if we talk about the twisted pair, so these are the frequency ranges, right? So that's why you can see that voice falls in this frequency range. So it's very native in order to convert our voice into the electrical pulses and to transmit that voice over the twisted pair. And this is the attenuation, 0.2 dB per kilometer at 1 kilohertz. And we also have the delay, that is also an important factor, 50 microsecond per kilometer, that is the delay. And we need a repeater after every 2 kilometer for the twisted pair, right? So if you want to transmit, for example, voice by using this twisted pair as a medium, so you need a repeater after every 2 kilometer. Then we have twisted pair, but here we have multiple pairs, right? We don't have single pair, so this is the single pair, and here we have the multiple pairs. The frequency range, obviously it rises 0 to 1 megahertz, so here we have kilohertz, and the attenuation is 0.7 dB per kilometer, and delay it reduces, right, 5 microsecond, and repeater spacing is the same. For coaxial cable, the frequency range is on the higher side, 0 to 500 megahertz, and the attenuation is also on the higher side as compared to the twisted pairs, right? So it's 7 dB per kilometer delay, right, 4 microsecond, and you can see that we need repeater at a longer distance, right? So the distance between repeaters is 1 to 9 kilometer, right? And then we have the fiber optical fiber or fiber optics, right? So here the range is on the much higher side, 186 to 370 terahertz, and the attenuation is also lower, 0.2 to 0.5 dB per kilometer, and delay is 5 microsecond, right? And you can see the repeater spacing, it's again on the higher side, 40 kilometers. So it means this can be useful media if we want to have data transmission between different cities, right? So these are the transmission characteristic of guided media. So here we have shown different guided media graphically, right? So twisted pair, coaxial cable, and optical fiber. So let's talk about twisted pair, right? So you can see that we have a pair of wires and they are twisted, right? See, so the reason for those twist, if we have a single cable, so it introduce EMI, electromagnetic interference. If we a single pair of cable without twist, so each cable it produces EMI, that is electromagnetic interference. So as a result, the data can be distorted, or there can be some noise, or we can have errors regarding the data communication. So we have twisted the pair in such a way that EMI for one cable is cancelled by the EMI from the other cable, right? So this is the reason for giving twist to this pair, right? So you can see that in the black we have a single cable, and in the other color we have another pair, and they are being twisted. And moreover, they are insulated separately. We have insulator for each cable, right? And we can have also bundles of those pairs that are being again packed into a single cable, right? And these are being used in buildings, right? So these are the transmission characteristics for twisted pair. So if we have analog media, right, then it means we need amplifier. If we are going to transmit analog data, right, over the twisted pair, then we need amplifier after every 5 to 6 kilometer. If we are going to transmit digital data, right, so we can use analog signaling as well as we can use digital signaling, right? So we have already studied that we can use different representation of data. If, for example, if we have a digital data, we can use analog signaling as well as we can use digital signaling. And in this case, we need a repeater after every 2 to 3 kilometer, right? So the repeater distance has decreased in case of digital data transmission. these are the limitations, right? Distance, the bandwidth, and the data rate. Obviously, we have already discussed those different parameters. And additionally, twisted pair is more susceptible to interference and noise because of the cancellation of EMI. They are more immune to interference and noise. So here we have the comparison, right? We have two different types of twisted pairs, unshielded and shielded, right? So in case of unshielded twisted pair, that is called UTP, we can use that UTP in ordinary telephone communication. It's cheap as opposed to STP or shielded twisted pair, and it's easier to install due to its flexibility, and then it can also introduce external EMI, electromagnetic interference, not internal, because internal is being cancelled with each other, right? And we can splice it easily. On the other side, shielded twisted pair or STP, it has a metal braid or sheathing that reduces interference, right? And it can provide better performance, and it can transmit more data, higher data. It's more expensive, of course, and it's due to its thickness, it's difficult to handle. And then here we have different categories and classes of twisted pair, right? So here we have category 5, class D, category 6, that is class E, category 6A, that is class EA, category 7, and then we have category 7A and class FA. So here we have the bandwidth, right? So for different categories we have different bandwidth, right? And these are the types of cable, UTP, right? UTP, and here we have the insertion loss in dBs, next loss in dBs, right? And ACR in dBs. So you can see that for Cat 5 we have bandwidth. It can support 100 megahertz bandwidth, and the type is UTP. Insertion loss is 24 dB, and next loss is 30.1 dB, and ACR is 6.1, right? For Cat 6 you can see the bandwidth it can support rises, and the insertion loss decreases. So if we talk about this Cat 7A, it can support the maximum bandwidth, right? And the cable type is S, right? This means shielded, and FTP, foil twisted pair, and the insertion loss is again on the lower side. Next loss is 65 dB, ACR is 44.1. So this is a sort of comparison, right? So if you want to choose, want to pick, so first you have to draw the link budget, and then you need to look at your requirements. Then you can choose one of the cable which is required, right? So normally these are available at a cheaper price in the market, right? For example, nowadays Cat 5 is Cat 7 is very popular for computer network communication, and we say this is a sort of gigaspeed cable. Okay, and then there are certain sort of impairments or bottlenecks that are associated with each media, right? So let's talk about the crosstalk for the twisted pair, right? So as if we have a lot of different twisted pairs, so the coupling of signal from one pair, right? So the induction from one pair, right, can affect or can produce an EMI, right, for the other pair. So as a result, we can have a crosstalk, right? So whenever we talk about the voice communication by using twisted pair, right? So the current flows from source to destination, and you can also say from if we have a transceiver on both sides, so we can they can send and receive at the same time, right? So you can suppose that we have a transmitter and a receiver, and we are going to transmit the voice by using the twisted pair. So whenever voice will traverse the medium from from sender to the receiver, so as a result, the current will flow through this twisted pair. So as a result, whenever the current will flow, electrons will move from source to destination. So as a result of the movement of electrons, there will be coupling of electric field and magnetic field. So that coupling can be induced by the other pair, some other pair, right? So there can be a crosstalk as a result of this coupling, right? So we normally this happens whenever we have communication by using normal PSTN lines, public switch telephone network lines, right? So you can see we are talking to somebody, and suddenly we come across some crosstalk, right? So okay, and this is also important, right? Signal power relationship for twisted pair characteristic. So here we have the scenario which I have mentioned, right? So of course, if we talk about telephone set, so it can receive and send voice, right? So we have a transmitter, we have a receiver as well. So this is system A and system B, right? So this is the transmitted signal. So the power of the signal is PT, and here we have the received signal, right? Or you can say its power has to be reduced, so we have mentioned PR, reduced power, right? And then again you can see this is the transmitted signal, right? So here the transmitter is fed to the receiver, and here transmitter is fed to the receiver on the other side, right? So data will flow from transmitter receiver, for this transmitter to receiver, right? So this is the you can take the example, or you can imagine the telephone set that are being connected by using this twisted pair, right? So we can also have the relationship between next loss and insertion loss, right? At system A here, a transmitted signal from system B. So here we are transmitting, and here we have the receiver for the moment. The power is PT, that is transmitted power, is received at A with a reduced signal power of PR, right? So in the subscript you can see PR. So at the same time, system A is transmitting to signal B. So A is also transmitting. So of course you can see that we assume that the transmission is at the same transmit signal power of PT. So from here we have the same signal. So due to crosstalk, a certain level of signal from A's transmitter is induced onto the receiver wire pair at A. So this is the receiver wire, and this is the transmitter wire. So there is an induction, right, due to the EMI, So of course, for having a good quality of sound or good quality of communication, the reduced power should be greater than the PC, right? That is the induced power, right? So in order to receive the signal in a good way, right? So this is the condition, right? So the PR should be greater than PC. Okay, and these are the connectors that are actually being used for UTP, unshielded twisted pairs, and you can see they are actually RJ45 connectors, and we have male and female. So here we have RJ45 male connector. You can see we have 8 different wires, or you can say 4 pair of wires. For the RJ45 female, you can see we again have the 8 wires and 4 pairs, right? So we can have different sort of configurations. For the state cable, right, we have the state connection between devices, right? So it means one will be connected with 1, 2 will be connected with 2, and so forth, and 8 will be connected with 8, right? So for the cross connection, we will be having some other configuration, like here you can see that the transmitter is connected with receiver, and here receiver is connected with transmitter. That is the cross connection, right? So here again, if we have mentioned over here, we have to connect this device, that is the male connector, right, to this device, that is the female connector. So if we have a transmitter at 1 and 2, right, so we have to declare, or we must have the information where the receiver is here, because here we can have transmitter and receiver, right? So you can see if we have transmitter over here 1, 2, and we have a receiver at 3 and 4, right? So you can see we will be connecting 1 and 2 with 3 and 4. So if we have a transmitter here at 5 and 6, so we can define, or we can have the receiver here at 7 and 8. So it's again depending upon the configuration of the interconnecting devices. We can also have another connector that have 2 pair 4 wires, that is RJ11, and that is very commonly being used in case of telephony. Okay, so here we have different applications of twisted pair cable, right? So as I have mentioned that the twisted pair cables are used in telephone lines, and those telephone lines, they are actually being used for voice and data communication, right? As we can also use those twisted pairs in order to connect DSL lines to central exchanges, right? And we can also use those twisted pairs in order to interconnect different computers and other devices like switches and routers for local area networks and wide area networks. And okay, so let's talk about the coaxial cable. That is another type of guided media, right? So you can see that we have shown here a typical coaxial cable, right? So we have the outer shielding, and here we have inside this circle we have outer conductor, right? And then we have the insulation that is shielding this outer conductor from the inner conductor, right? So here we have the inner conductor. So the outer conductor is a braided shield, inner conductor is a solid metal, or you can say a solid metal wire, and we have an insulating material in between. Okay, so this is the real coaxial cable, right? So you can see that we have a foil here, right? So and then we have shielding, insulating, right? Insulator, and inside we have another conductor. So A, outer plastic shield, B, woven copper shield, right? And then C, inner dielectric insulator. This is the insulator, and at D, this is the copper core, right? So here again we have model this plastic jacket, right? This is another sort of coaxial cable, and then we have metallic shielding, right? Dielectric insulator, and this is the core conducting cable. Okay. So they are actually being used for transmitting video as well as radio signals, and we can also use coaxial cable for high-speed data connections. Okay, so depending upon the material, it can support different frequencies. So of course, if different frequencies, so we can transmit different data. Okay, so these are the transmission characteristics of coaxial cable, right? So in case of, you can see, it is more superior as compared to twisted pair. So it support much higher frequency as compared to the twisted pair. If we talk about the performance, right? So the only limitation or the bottleneck is the attenuation and the noise, right? If we have analog signaling, right? So for analog signaling, and we are using coaxial cable, right? So amplifiers are needed after every kilometer, right? And the spectrum is close to 500 megahertz. For digital signaling, right? Repeaters are again required for every kilometer. Okay, so these are the connectors, as we have studied connectors for twisted pair. So these are good connectors for coaxial cable. So it is called a BNC connector. So you can see this is the cable, right? So this is the BNC connector. We can also, if we want to cut and connect the coaxial cable, so we need a T-type BNC connector. So this is the T-type BNC connector. So here you can see that if the cable is going like this, and you want to cut and connect, right? So you need a T connector over here that will fit, connect those cables, and we can have a connection from here, right? So this is a suitable scenario when we talk about the bus topology, right? So again, we have certain advantages and disadvantages that are being associated with coaxial cable. So of course we can have data transmission at a greater distance, so it means we need repeaters after longer distance as compared to the twisted pair. And thick coaxial cable, it has extra protective shielding, right? So it means it's more secure, right? So the advantages includes due to its thickness, it's very difficult to install, right, as opposed to the twisted pair. Okay, so now come to the fiber optics or optical fiber. So you can see that we have a typical optical fiber over here. We have a core that is made of a fiber, transparent fiber, right, flexible fiber or high quality glass, and then we have a cladding, right, and here we have the jacket, right. So glass or plastic core, right, okay, and this is the transmission, how the data is transmitted within the optical fiber, right. So light at less than critical angle, so whenever we have to insert the light, we have to throw that light at an angle that is less than the critical angle, right. Right, so and then this is the angle of incidence, angle of reflection, right. So here if the angle of incidence and angle of reflection, right. Okay, so we can use various glasses and different type of plastics in order to construct a fiber, right. So you can see its cylindrical shape, right. So this is also a cylindrical shape. This is also core, cladding and jacket, they all have cylindrical shape. So one of the big advantage of optical fiber is that we can have communication, data communication as at a much longer distances, right. Okay, so these are the benefits. It support very high data rates in GBs, gigabit per second, smaller in size, right. So as we are using plastic, right, or glass, so it is much smaller in size and it having a lighter weight as compared to twisted pair, which where we use metal. Lower attenuation, right, and as light don't have any electrical charge, so whenever light moves or photons move from source to destination, there is no electromagnetic interference or there is no electromagnetic isolation. So we have greater repeater spacing, right. So for example, we have a source and destination, so depending upon how much source and destination are, we need very few repeaters as compared to coaxial cable and twisted pair. So these are the transmission characteristics. So we use the principle of total internal reflection in order to transmit light, right, and in order to convert data into light, we use light sources, LEDs, light emitting diodes, and then we have a injection laser diode, right. So those all have relationship among wavelengths, type of transmission and achievable data rate. So we have different modes of propagation. When we talk about the optical fiber, we can have multi-mode propagation and we can also have a single mode propagation. For multi-mode, we have step index and graded index. So here we have shown different transmission modes, right. So here in multi-mode, step index, light from a source. So here we have the source, right. So it enters the cylindrical glass, right. So this is the cylindrical glass, right. We can only show here like this. So rays at shallow angles are reflected and propagated, right? So you can see that these are being reflected and propagated along the fiber, while the other rays are being absorbed by the surrounding material, that is, right? So this form of propagation is called step index multimode, right? And then we have single mode fiber, right? So when the fiber core radius is reduced, so you can see, and then the radius is reduced over here. So we are left only with fewer angles, right, where we have reflection, other are being absorbed, right? So this is single mode propagation, right? So it provides superior performance due to some reasons. Single transmission path, right? Single mode transmission. The distortion found is in multimode cannot occur. So here we have more distortion, but here, as we are having only single mode propagation, right, and single transmission path, so we don't have any sort of distortion. And then here we have graded index multimode, right? So you can see that intermediate. So here we have reduced radius, right? So here we have high radius, and this is in between. So this sort of configuration is called graded index multimode. So we hide the refractive index, right, at the center, makes the light rays moving down the axis advance more slowly than those near the cladding, right? So you can see that the light rays that are near the cladding, right? Okay. So these are again the propagation modes. We multimode step index, right? So there are more details. Multimode, we can multiple beams from a light source move through the core in different paths, right? Density of the core remains constant from the center to the edges. A beam of light moves through this constant density, right? So this is the case of step index fiber. So graded index fiber, highest at the center of the core and decreases gradually at its lower at the edge, right? So if I go back, so for graded index, we can see that the density is higher at the middle, right? But it reduces at the edges. Okay. So here we have shown a table mentioning the range of wavelength, right? And then if you can see its support label we have made regarding the band and the type of the fiber and its application, right? So here we have the wavelength in nanometer, right? 820 to 900 nanometer, and this is in terahertz, very, very high, 366 to 333, right? And multimode fiber, and the application, we can use this in LAN. So wavelength is increasing and the frequency is decreasing, right? So you can see 234 to 222, band is S, single mode, and it has various applications, right? And then we have wavelength on the higher side and frequency is lowered here. Band is C, single mode, and application is WDM, wavelength division multiplexing, right? Okay, so these are the connectors, right? So in order to connect different devices, right? So nowadays you can have fiber optics as a last mile, right? So whenever somebody wants some service, for example, high-speed data services, so the fiber are being used for the last mile from the exchange to the subscriber's destination, right? So previously we normally use copper cable for the last mile communication, and that was proving the real bottleneck, because even if we have fiber optics or whatever the high data transmission media at the backbone, but the last mile proves to be the bottleneck, right? But now it has changed, and we can have fiber optics because the devices, connectors, and other facilities required in order to lay the fiber optics, they are becoming cheaper and cheaper and available, and the technology is being absorbed. We can have different technology experts, right? A lot of technology experts that can terminate fiber at the user's premises, right? So here we have the advantages and disadvantages of the optical fiber, right? So first, one of the big advantages, it can support more bandwidth, right? So it means we can have huge data rate, right? And then low power loss. That's why we need repeaters at a very, very long distances. As I've mentioned, that because light is traveling for data communication, right, as opposed to the electrical pulses, right? So the interference is very, very low, right? And then the size, right? So the size is very smaller, and weight is also smaller. Safety, security, and flexibility, right? So if you talk about the security, so it's very difficult to cut the fiber and to receive the signals, because you need a very specific sort of arrangement in order to tap, right? And then we can also have flexibility. And the disadvantages, of course, cost. It costs more. So this is also one of the disadvantages, right? So fragile, whereas we use glass and plastic fiber, plastic, right? As so it's fragile. Okay, so let's talk about wireless transmission frequencies, right? So before we have discussed guided transmission media, so let's move to the unguided transmission media, right? So that is the wireless transmission media, right? So we should be aware of the frequencies that it supports, right? So if we talk about 1 gigahertz to 40 gigahertz range, right? So these frequencies, they are referred to as microwave frequencies, and they are actually highly directional beams, right? And this sort of communication or this sort of propagation is suitable for point-to-point transmission, right? And they are being effectively used for satellite communication. Then we have 30 megahertz to 1 gigahertz, right? So they are suitable for omnidirectional applications, right? And this is actually, this range is referred to as radio frequency range. And one of the example is the cellular communication. Then we have infrared portion, and that is 3 into 10 to the power 11 to 2 × 10⁻14. So we have an infrared portion, right? And this is actually useful for point to point, right? For example, within a room. Okay, so this is the spectrum, right? So we have shown the electromagnetic spectrum for telecommunication, right? So you can see we have different frequencies, and we have marked them like extremely low frequency ELF, medium frequency MF, UHF, ultra high frequency, and then we have voice frequency VF, HF high frequency, and SHF super high frequency, right? So VLF very low frequency, VHF very high frequency, and EHF extremely high frequency, and then low frequency. So you can see that for twisted pair, right, we have ELF, right, it covers from ELF to VHF, very high frequency. For coaxial cable, it start from VLF, right, or you can say VF, and it ends up till UHF, ultra high frequency. Then we have AM here, FM here, and this is terrestrial and satellite communication. So this is the portion for infrared and laser, and here we have the visible light and optical fiber, right? So wavelength is decreasing over here. Okay, in order to have communication, we need certain components, and one of the main ingredient of communication is antenna, right? So actually an antenna is a device that converts electrical signals, electrical power, or waveforms, electrical waveforms into radio waves, and vice versa. If we talk about the receiver, it will receive the radio waves and will convert those radio waves into the electrical pulses. But nowadays we have antenna that can be a receiver as well as can be a transmitter, right? So we can have a transceiver and sort of antennas. Okay, so here we have the transmission antenna. So as I mentioned, we have both capabilities in a single electrical device, right? So radiated into surrounding. So transmission antenna, what it does, it radiate into the surrounding, and it convert electromagnetic energy, right? So in order to transmit, of course, you have to transmit the electrical pulses, right, into the radio waves. Okay, for the reception, we the receiving antenna, right, it is being receiving, right, converting radio energy into the electrical pulses or electrical energy. Okay, so we have different type of antennas, omnidirectional, directional, right? So in order to characterize the performance of an antenna, we need to know the radiation pattern, right? So some antenna, they radiate in all directions, omnidirectional, and but they does not perform well in all directions, right? So the example you can say, whenever we talk about the cellular communication, we have an antenna, for example, at the tower, and that antenna is transmitting in a certain cell, right? So if we have a cellular phone, so and we are within that cell, so we can receive signals from that antenna, right? So then we have an isotropic antenna, and is a point in space that radiates power, right? So that is so this is another example of omnidirectional. In all directions it radiates power equally, right? So with a spherical radiation pattern like here. Okay. Then we have parabolic reflective antenna, right? So this is the example, and those sort of antenna, they are being used in microwave and satellite communication, right? So here you can see that we have a parabola. This is the focus, right? So you can see if I swap it in such a way, right? So it can be like this. So here we have a focus, right? And then we have a cross section of parabolic antenna showing reflective pattern, right? So you can see that how the radiations are being reflected, right? And then we have certain parameters that are very important whenever we talk about the antenna design. That is one of the important parameter is the antenna gain, right? So it actually measures the directionality of the antenna. So particularly the output power, right, in a certain direction versus that produced by an isotropic antenna, right? So it is antenna gain is calculated in decibels, right? And it results in loss in power in another direction, right? But, and moreover, a plot of the gain as a function of direction is called the radiation pattern, and we have here radiation pattern. Okay. So here we have microwave communication, right? A system or a method, right, or a technology or service such as multi-channel, multi-point distribution service that utilizes microwave line of sight communication between sender and the receiver, right, located on the ground or on towers, as opposed to the sender and receiver antenna being located on a communication satellite, right? So the uses of this sort of microwave, terrestrial microwave, right, are telephone, TV, or data services, right? So the example is a parabolic dish with an antenna focusing a narrow beam onto a receiving antenna, right? So here we have the applications of terrestrial microwave. So these technology is being used for long haul communications. It can also be used for short point-to-point links between buildings and cellular systems, and we can have very small circular antennas that are pointing to another tower and having another antenna, so we have point-to-point communication. We can also use this for voice and TV transmission, right? And the main source of loss is attenuation. This is the bottleneck, mostly by distance, maybe due to weather also, right? So here we have bandwidth and data rates for microwave, right? So this is the band in gigahertz, bandwidth in megahertz, and data rate, right? So band 2 gigahertz, and this is the bandwidth, right? And here we have the data rate in megabits per second. So here are 18 gigahertz, and the bandwidth is 220, right? So this is the effective bandwidth, and here we can achieve the data rate of 274 megabits per second. Then we have satellite microwave, right? communication satellite is in effect a microwave relay station, right? It is used to link two or more ground stations, right? So we have a satellite in space, right? And we can use microwave communication via this satellite in order to connect two or more ground stations that are being right on the ground. So effectively we can have a greater vision or greater coverage area when we are in space, right? So receives on one frequency, right? So one frequency is being used for receiver, downlink, right? And then it amplify it and repeat the same signal and transmit at another frequency, right? So there are two different frequencies, one for uplink and the one for the downlink, right? And we requires geostationary orbit because Earth is rotating, so we need to adjust its rotation and movement in order to have communication by using satellite microwave, right? So here we have a scenario, point-to-point link, right? So we have a satellite antenna over here, right? And you can see that Earth station, this is the transmitter and this is the receiver, right? So those two ground stations that are being lying on the Earth, they are being connected by using this satellite, right? So this is the transmission and here we have the reception. So you can say that this is a sort of point-to-point link if we have assume that we have an antenna, right? So point-to-point. And then we have the broadcast, right? So the satellite is broadcasting, right? So this is the transmitter, right? And then the satellite is broadcasting and it is being listened by all the receivers, right? So we can have the dish TV receiver is the best example, right? And where we multiple receivers are receiving the satellite communication, right, on a certain band. So these are the applications of satellite microwave, right? And businesses, right? And then the television distribution, right? And then the GPS, global positioning system. They are actually using satellite microwave communication. These are the transmission characteristics. The optimum frequency range of satellite transmission is 1 to 10 gigahertz, right? And satellites, they normally use frequency bandwidth range of 5.9 to 5 to 6.4 to 5 gigahertz from Earth to satellite uplink. So this is the frequency for uplink, and then we have a range for the downlink, right? So as I've mentioned, we have an uplink and we are using one frequency for uplink, and then we are using another frequency for the downlink. And here we have the broadcast radio, right? Between broadcast radio and microwave is that the former is omnidirectional and the later is directional, right? So thus broadcast radio does not require dish-shaped antenna, right? And antenna need to be mounted, right, to a precise alignment, right? Okay, so here we have FM radio, right, and UHF, ultra high frequency, VHF, very high frequency. For omnidirectional, we have limited line of sight, and the bottleneck is multi-path interference. And here we have the infrared. For example, we can have the example of a TV remote control, that is a device which is using infrared spectrum. So that is summary, right? So today we have discussed transmission media. I mean, talked about guided and unguided media, and we discussed different advantages and disadvantages of some of the media. For example, twisted pair, and in the twisted pair we have shielded twisted pair and unshielded twisted pair. We have also mentioned different categories of UTP, and then we talked about coaxial cable, the advantages and the disadvantages the coaxial cable having over twisted pair, and finally we talked about optical fiber, right? And then of course there are different design factors that are being involved when we talk about the media. So we discussed those design factors, different parameters that are being associated when we have to choose the media, and we have to correlate the media with the transmission and the reception. And one of the important component that is involved in communication, especially the wireless communication, is antenna. So today we talked about the antenna, right? Its different parameters and factors, and finally we discussed about the different propagation modes that are being adopted when we talk about the wireless communication. So that's all. अपना ख्याल रखिएगा. अल्लाह हाफ़िज़. अस्सलाम वालेकुम.